Assalamualaikum warahmatullahi wabarakatuh. So chapter 6 inshallah. So we will be covering example 6.1 until 6.3 in the textbook and also 6.5. Right. So this is an extending of the what you have seen earlier when in subtopic of 4.5. Okay, 4.5. Now let us turn to the book. Okay, whatever you have understand in previous subtopic 4.5, it's still valid. It's just that for this subtopic it go slightly lengthy. Okay, so in connection to what you have seen earlier, to expand the idea, so we are now looking at the idea of the forces. With the idea of the forces. So previously we are talking about our discussion most of the time in chapters 4.5 will be on the acceleration. If you recall, there is A tangent, AC, and then there will be A total, okay, where the system is moving at a constant V value, or perhaps V is changing, right? So in here, we are now looking at the concept of the force itself. Now, in parallel to what you have seen earlier in the concept of Newton's law and the generic idea that if you have an object move in a circular motion, hence there will be an acceleration towards the center, which is called as centripetal acceleration, so towards the center. And you will find that this AC and the V tangent are perpendicular with one another. This is the term that they are trying to describe the concept of the direction. So this is the tangent just now, circumference, tangent to the circumference, and we will find that AC is always directed towards the center, as this figure as well, 6.1, and here as well. Okay, and in both case, okay, when we relate with the idea of the force, since you have acceleration, the correlation with the force, which is chapter 5, should be a product of MA, and therefore MA turns to be mv squared over r, combination of acceleration v squared over r. And the idea that we are going to look here is the centripetal force is the force responsible, bertanggungjawab, menyebabkan the object move in a circular path, and therefore the moment dia break, the string break, then it lose the ability to move in a circle. So where would it go? Tangent to the circumference, because that is the inertia during that time. So at that moment it's trying to move in the tangent, but yet being pulled towards the center, and that's why the V slightly change direction because of the centripetal force. Keep pulling it, making a curved path along the way. However, now the force is not there. Take it out, and that's the reason why where it will continue in the idea of Newton's first law and moving in the tangential direction. Now, this is an example how object travel in a circular path and show that the velocity is always tangential to the circumference. And you will find that, okay, the centripetal represent concept of center seeking. That's the direction of force. And yes, so as you cut it, the force that supply the centripetal force disappear, the object will move in the tangential direction. Now let's turn to example 6.1, the conical pendulum. The term is conical because the pendulum, as it rotates, it resembles the shape of a conical. And given here, a ball labeled as M, okay, is hung by or suspended by a string with length L, and then it revolves with a constant speed in a horizontal circle as shown, and with a radius of r. Okay, a radius of r. Then it says that you are to find an expression V, where in the expression there should only be symbol length L and the angle with the vertical. Alright, now, so notice that in this example, what we are expected to do is, we are going to identify, number one, identify our FC. Okay, what are the forces? What are the forces that contribute to the centripetal force? Okay, that's our first task. And then from there, we are going to open up the expression into mv squared over r. And then later on, the third task is to rearrange the expression or simplify into expression v equivalent to something, which is unknown. Alright, so let's start with the first one. Now, according to the figure, there are two forces here. Number one is tension because a string there. Number two is weight. Okay, no issue, right? Weight is obviously in the y direction. So it would not contribute anything in the x direction. Why x direction? Because this is the direction of the centripetal force towards the center. So no, mg would not supply centripetal force. So let's now look at the tension. So we notice that open up the tension, T cos theta, T sin theta, will give us this T sin theta as equivalent to the centripetal force. Now ask yourself why? Because it pointed towards the center. Okay, now that we know that T sin theta is the force responsible ataupun itulah centripetal force. Okay, the next issue is how is it that it jot down as T sin theta? Okay, so you might get a bit confused there. Notice that look at the angle given. Okay, this is the theta. Now if I were to draw in a form of zigzag, then you will find that, oh, okay, this is the theta that we are talking for. So we find that this is T cos theta. If let's say this is 30 degree, then this is T sin 30, example. And therefore, this should be T sin theta. Okay, and again, we are trying to say that T sin theta is the centripetal force. Alright, so let's put the answer. This is T sin theta. And from here, we are going to equalkan dia with mv squared, and then we are going to rearrange them. Why? Because the question is asking, please state the expression of v, or simplify the expression and then solve or calculate v lah. In a normal scenario for the exam is calculate v. Alright, so look here. Okay, we are here at equation number 2 actually. T sin theta is the centripetal force. And then centripetal force is mv squared over r. Now that you've seen it in this version, your next task is to simplify. So as you simplify, you will find that the expression would turn out to be T sin theta is mv squared over r. Now, what's next is to make a few things disappear, okay, or replace. Why? Because they want it together with the length, and you find that in the expression there is no length. So how are we going to relate length into this expression? Is by changing r. So our next aim is changing the r symbol. Alright, besides substituting r, replacing r, we are as well replacing t. Okay, replacing t. So there are two things that we are going to replace. Now, how to do first? Number 2, okay, because it's much easier. Look at in the y component. Okay, in the y component, what we are going to do, this expression, we are going to isolate t. So arriving with mg over cos theta. So this is to be substituted here. And from your substitution, turns out that something like this, over cos theta times sin theta equivalent to mv squared over r. Mv squared over r. So sin and tan, when they are combined, sin and cos, when they are combined, sin divided by cos, it becomes tan. And then m can be cancelled out. Right, writing it once again, we have g. And sin divided by cos become tan theta. On the right side become v squared over r. Okay, we are almost done. If we notice that in the expression we do not see r value, r symbol. So our next task is to substitute r value. So here, have a look. This figure, the green figure, is drawn from this figure. This is the length and this is the R. Okay, the R. And to substitute R, replacing L, okay, so we are going to see that R is equivalent to L sine theta. And that's exactly what we are going to do for this question. And here is L sine theta. Okay, right, everything look a little bit. So simplify it, G times theta. Okay, this is the V squared just now. And over R now being replaced with L sine theta. Right. Your next task is rearrange it into this and isolate or simplify as V is equivalent to. So you will find that it looks something like this. L sine theta times G tan theta. Okay. And similar. Okay. It's just that square root the value. Okay. Now, at the end of the day, the aim of this example is just number one, okay, to get the centripetal force. To understand the centripetal force is any force that's directed towards the center. It could even be more than one. It could be even more than one, okay, where they will interact with one another and the net force would be the centripetal force. But in this case, there's just one singular force and it's just tension product, which is T sine theta. That's number one. Number two, since now we know that it's the centripetal force, that's the reason why we can equip it with mv squared over r. The next is just mathematical. Okay, it depends on the values given in the question itself. Okay, so if let's say that you have theta and you are going to substitute and simplify, get the r value. Okay, so don't worry so much that if you keep asking, don't memorize this expression. This is actually subjected to question. Okay, and the aim are just 1, 2, 3 just now. Alright, this is not something that come from your textbook, but it's very interesting to look and learn something from this. Okay, this is a situation whereby astronauts spend a lengthy time in the outer space where they will experience the negative effect due to the weightlessness. We thought that less weight, less force of gravity would be best. But turns out that the body is so brilliant that it detects that there is no need of calcium, and hence, okay, there will be loss of calcium in the bone. So the bone deteriorate and weakening of the muscle tissue. So you're not moving around, okay, you're not feeling the gravitational force, and hence the body simply getting less effective. So what they did is they create an artificial gravity, okay, so that this astronaut can keep on experience the force, the gravitational force. So how does it look like? It's a very similar to our washing machine, okay, a big cylinder and keep spinning. So as you can see in this figure, the astronaut will be pressed onto the inner vertical wall, and the pressing will be equivalent to what you simply call as the normal force, and they will arrange so that the normal force will be equivalent to the value of the gravitational force. So they will manipulate in terms of the spinning speed, and so that the normal force would just equivalent to the in this case, if I can jot down, okay, so the normal force is the centripetal force, and therefore the manipulation of the speed and also the size, the R of the cylinder. So if they can manipulate the two value of V and R, so that at the end of the day equivalent to the product of mg at least, okay, and therefore there will be equivalent to the as if they are still on Earth itself. Now let's turn to the book itself again. Example 6.2. How fast can it spin? A puck, okay, a hockey puck perhaps, attached to end of a cord, 1.5 meter long. So we can say is that this is the radius. Okay. After this, we're going to draw it, or perhaps figure examples that have figure. And the puck move in a horizontal circle as shown in figure 6.1. Alright, we have seen this figure previously. So if the cord can withstand a maximum tension of 50 Newton. So this is tension towards the center. Towards the center. So the drawing will look something like this. And the string is directed here. So this is where the puck is. And you will find that, tension is the centripetal force. And the maximum value is 50 Newton. What will be the maximum speed? Okay, since this is the maximum force, when we equip it with mv squared over r, therefore this v will respond the maximum v. Meaning that exceeding the value of this value, 12.2 meter per second, definitely the string will just break. So that is the idea. Okay, let's quickly revisit the figure itself. Okay, so the figure is drawn from above. So overhead figure, overhead view. And you find that the whole idea is towards the center is the centripetal force. And something to note as well, okay, that might confuse you a little bit is that rather than writing FC, the book choose to write it as FR. Now, you can freely cancel this, write it as FC, because the idea is not that the direction. The idea is this F towards the center is the centripetal force. Okay, so if it confuses you, it's okay. You can just write it down as FC. Okay, but in this case, in this figure, it's trying to say that FC and FR is the same in terms of magnitude, and therefore they are replacing the symbol here. Okay, but remember back then that FR is away from the center. It's the opposite, but they are of the same value. So if along the way you get confused, just go with the idea towards the center is the centripetal force. And this is something to ponder, that since tension is in the same direction towards the center, and therefore tension is the centripetal force. That's the essence of these two figures. Alright, let's continue. So jotting down the process is like this. Okay. So 50 then. Okay. 50 then is equivalent to mv squared over r. And let's just substitute certain numbers here. R is 1.5. Why? Because it's equivalent to the length. R is equivalent to the length of the string just now. Mass is given as 0.5. Okay. And the question is asking for V. Right? So solve it. So you should arrive with the same answer as provided. Alright, let's look at the what if. Suppose now it travel or move in a larger radius, but same value of V, same value of speed. Would it break or not? Would it break or not? Okay, now this type of issue require this understanding that the T maximum that it can withstand is still 50 Newton. Okay, now so our task is to calculate our FC, whereby our FC will arrive with the tension during the new R. Let's say that it's just 2R perhaps, okay, a larger value of R. So with this process, we are arriving with the expression that mv squared over R. Okay, and by changing the R value, okay, let's say that now we introduce 2, okay, so you will notice that overall product of the this expression will be 1 over 2 of the T at original value, okay, T at T max earlier, half of it, T. So you might be arriving, in fact, the calculation will become 25. Give it a try, okay, give it a try. Now, 25 is less than 50 Newton. So that's the reason why, okay, when you change into the bigger radial, the acceleration will be smaller and required tension which is smaller. Tension becomes 25 for our calculation just now. So resulting situation where the string will be less likely to break when R is larger. Right, now let's have a look at example 6.3. What to expect from this example is number one, when you make a turn, when a car negotiates a turn, there will be one force towards the center, and that force is static friction force. So you need then to memorize again that static friction can be calculated by using expression coefficient times the normal force. And since it's static, coefficient static. Alright, so this is given by your book where here, okay? And therefore, since it's directed toward the center, pulling the car so that it does not move in the tangential direction, okay, means that this is the supply centripetal force. This is the supply centripetal force. This is FC. So according to the question, if the radius R value is this much, and this is the mass of the car on flat and horizontal, we are not going to do banking. Banking ni maknanya dia incline, tak ada. Dia flat sahaja. So flat that you must understand and recall and memorize is towards the center is the static friction, and static friction therefore is equation coefficient times normal force, and centripetal force, yes, wajib. Right? So the question is, if the mu coefficient, mu is 0. So this is coefficient. So coefficient is mu. Find maximum speed. So they want the maximum V value that the car can safely negotiate the turn, right? And for that case, so we are looking at a situation that what is the Fs maximum, okay? And during this time, you will find that this Fs is now equivalent to mv squared over R. Since this is the supply maximum friction, therefore the corresponding V, calculated V nanti, is the maximum V product, okay? And this is what you seen from my earlier, okay? And here, okay, from the Y component, since it's on a flat surface, the value of N normal force is the mg. In fact, even if you do not show it, straight away you can go towards the idea that normal is the mg, enough, okay? So you don't start from here. So it's enough, and then from there, you are going to substitute the value of N into the expression. That's one. So this would be equivalent to mg. This is exactly what they did just now. So hence your equation turns out to be coefficient mg equivalent to mv squared. Remember that the v is maximum because that just now the expression of Fs is resembling the maximum static friction can withstand. Right, and then R, so here goes with the simplifying the expression, and then when you put it as in V, you will arrive with this expression, similar expression as this one, okay? And notice, what the book provide you, they substitute with the normal, which is mg, and then simplified. So here lah, we are going to arrive with this one. Okay, what if we do not want it to be such? No problem at all. So just substitute the number from here. Coefficient just now is a product of 0, 5 to 3. Okay. G is, remember no negative no negative 9.8 because why? It's already embedded in the expression. So it's just a positive value. And then R is a value where 35 meter. And soft, what is your V? So you will arrive the same answer as provided. So in short, the car can travel only up to a maximum of 13.4. If it thus goes to 13.5, for example, then the car will skid. Okay, skid. Okay, begin to skid. So yeah, tangential to the circumference. If the question asks, if it does skid, in which direction? Tangential to the circumference. Alright, let's look at the what if here. Okay, this is a situation whereby now it's a wet day and the car turns out to skid when the speed is only 8 meter per second. Less than this, right? Less than this. Meaning that the surface changes and hence the coefficient changes as well. Understand? Because the surface now is changed into becoming wet, hence the value of coefficient become lesser or change in this case. So repeat the same process, it's just that the V maximum is now equivalent to 8 and you will arrive with the answer as 0.187. Okay, now let's do a comparison. So earlier the coefficient is 0.523 because why? This is just a normal and dry pavement or dry road, so it should be rougher. It should be rougher. In the case that it become wet, rain, okay, rain, hujan, so the coefficient become lesser. So it's actually, so indeed it's lesser as compared to the dry road. Okay, example 6.4, we are not going to do covering, we are not covering this one. So it now turns to example 6.5. Alright, in example 6.5, the situation is there is more than one force parallel to the direction of the centripetal force. So you will find that the situation required you to calculate net force, and this net force is the centripetal force. Understand? The net force is the centripetal force. Alright, in the given situation here, there is a small child with mass M on a Ferris wheel as in figure. The child moves in a vertical circle as in figure, and there are two locations of interest. Number one is at the top, number two is at the bottom. Now, in both cases, you will find that direction of the centripetal force will be as given. Okay, as given. And this is the resultant force. This is the resultant force. Now, if let's say that this child is traveling at a constant speed, which is 3 meter per second and a radius of 10 meter, determine the force exerted by the seat, which actually the normal force. The normal force. Why? Sit down. Okay, you are sitting down. Feel the seat exert force on you, which is the normal force. Alright. Now, according to the figure as well, for this object, for B situation, it is at the bottom. So this is this. So normal force is acting upwards, gravity is acting downwards. Same goes with when the child is on top. Okay. However, what makes them different is the direction of the resultant force. Resultant force in this case is the centripetal force. Centripetal force. So centripetal force in this case is when it's towards the bottom is a positive value. Okay. However, for the second figure, the centripetal force is directed downwards. So FC is downward. So the resultant force of these two forces is equivalent to negative FC. Okay, of these two forces. Now, therefore, when they are combined, we will find that mathematics, okay, of the resultant force here would be N, okay, upward, positive, minus wake is equivalent to FC. As simple as that. While for the second one, okay, still normal force because of the free body diagram. Normal force is positive, minus wake, but now it's equivalent to negative FC. Negative FC. Understand? Alright. Now let's do comparison with the answer with the book. All right. Okay, so at the bottom, normal force minus mg, but equivalent to positive Fc. So notice that is a positive Fc. Positive Fc, yeah? So, yeah, similar to us. Okay, double check. And minus is positive Fc. Alright. Now, how about when the location, okay, let's, from here, yes, you can do the calculation, substitute according to all the numbers just now. Okay, let's do the calculation. V is 3, R is 10, and what else? That's it. Okay, so this is 3, R is 10, okay. And from there, simplify, you will arrive with the normal force. Okay. However, notice that you don't have M. So, the question should be, express your answer in terms of the weight mg. So, leave mg as anonymous. Okay. As unknown numbers. Okay. Unknown numbers. So, this one. Alright, now when it is at the top then, okay, at the top, remember again it's the same forces direction. So normal minus mg. It's just that the net force is directed downwards towards the center. This is the center. So it's directed downward, and that makes it becomes a negative product. A negative product. Okay. So let's do comparison with this book. Okay. So, normal force minus mg is negative mv squared over r. Oh, madam, it looks different. This is positive because now times negative 1 to the expression. mg minus normal force equivalent to mv squared over r. So, now we have similar expression. Madam, can I not time with negative 1? I just like, from here onwards, I just substitute V is equivalent to 3, R equivalent to 10, and then I just simplify what will be the N. Is it okay, madam? Yes, it's okay. It's okay. So you can just keep this one straight away with your understanding that the resultant force is the centripetal force, right? And then from there, substitute and get the answer. We are at the end of chapter number 6 and 6.2 non-uniform circular motion is not within our syllabus, alright. However, it's to look at a quick look at it, alright. Notice that in this subtopic of non-uniform circular motion is whereby you will find that V is not constant. V is not constant, and when it's not constant, you will observe not only you have AC, you also have a value of A tangent. Why A tangent? Because this is a linear product. V changes, A changes as well. Okay. And in the case where V is constant, there is just a singular one value of A, which is AC, right? And something to just recall your memory from previous class, that A total combination of A, because you have AC directed towards the center. So this is a circular motion or a circular path. This is the direction of AC, and you find that AT is at the tangent, same direction as the V tangent. So as you combine then, you find that it's almost a shape of X and Y, and that's the reason why AT is added with AC in the version of calculating hypotenuse. Alright, to wrap up the whole topic once again, so the idea of the centripetal force that is equivalent to mv squared over r, you can see the synonym, or almost like previously we learned about acceleration only, then upgraded into Newton's law, and then upgraded into Newton's law again, but in the version of the circular motion. And here you find a few examples here. The basic example is trying to say that whatever forces in the direction, if you have a singular forces, one force towards the center, and in this example of conical is whereby you have to open up to the component, and that force towards the center is the centripetal force. That's the idea. And number two, in the case where you have a hockey puck, so there is just one singular force towards the center, and that is the tension, and therefore tension is the centripetal force. And finally, in the car negotiating turns, okay, ataupun sedang membuat pusingan, you find that ability untuk dia rotate tu is because there is static friction, the gripping of the tyre on the car, on the roads, okay, on the roads, and they have proven that that direction to the center is the centripetal force, and also equivalent to the static friction. So that's sum up the idea that static friction is the centripetal force, and then from there you play around with the expression. And finally, what if you have more than one force? So you find that you need to sum up or net force in the direction parallel to the centripetal force. And that summation leave you with equivalent to the centripetal force. And that's the essence of example 6.5. Alright guys, that's it for everything in chapter 6. Thank you very much.